Hello, everyone. I'm Ikhyun Kim. I'm a solution architect of simulation systems at Korea Aerospace Industry in South Korea. I'm honored to be here to introduce Korea Aerospace Industry and the Unreal Engine simulation ecosystem at this Unreal Fest 2024 series. So, in this session, I will talk about the latest trends in simulation that have changed with an advance of Unreal Engine and show you how Korea Aerospace Industry has merged its legacy simulation system with the latest trends. And I will also share our future vision for how we plan to utilize Unreal Engine in the future to develop sustainable simulation content. First is, here is Korea Aerospace Industry. You can call us just KAI. KAI is a total solution provider in aerospace. KAI also has been taking a leading role in the national aviation industry and security. We have satellite and the maintenance program, and also have Lovers and KT-1 program, FA-50, KUH-1 helicopters, there is a Flag Eagles, and next generation fighter jet, KF-21, is ready to flight. So, chapter 1 is a simulation ecosystem. I want to talk about how the simulation industry is shifting first. In recent years, the simulation industry has experienced rapid development, bringing about significant changes. One of the key changes is the shift to cloud-based simulation, which has greatly enhanced accessibility and collaboration. Cloud-based simulation provides access to high-performance computing resources from anywhere in the world, enabling seamless collaboration across remote locations. As a result, we can now perform more complex simulations faster and more efficiently while reducing our reliance on physical infrastructure. And digital twin technology creates digital replicas of physical assets that exist in the world, allowing their condition to be monitored and simulated in real time. This technology is primarily used in manufacturing, aerospace, and construction, among others, to reduce maintenance and operational costs and enabling predictive maintenance. And integrating AI and machine learning technologies into simulation has led to more sophisticated and predictive results. These technologies play a big role in anticipating problems that may arise during the design phase and finding optimal solutions through iterative simulation. Machine learning is automating data analysis during simulation to maximize efficiency. And virtual reality, VR, AR, MR, have greatly enhanced the immersion in training and simulation environments. These technologies are increasingly being used in highly immersive areas, particularly in aerospace, military, and healthcare, and are helping to make learning and training in real-world environments safer and more efficient. And simulation software is also starting to adopt microservices architectures. This approach breaks down the simulation process into smaller, independent services, each of which can be developed and deployed independently. This greatly increases the flexibility and the scalability of simulation software and allow for faster updates. These changes are moving the simulation industry from a simple modeling tool to a core technology that delivers complex engineering and simulation solutions. These trends are expected to evolve further and drive innovation across the wide range of industries. So let's look at the simulation ecosystem in Unreal Engine. Simulation team of Epic Games once said there are two industries that are leading the way in real-time 3D graphics, the game industry and the simulation industry. I agree with that, and I believe that Epic's Unreal Engine, which has been a leader in 3D graphics for many years, is not only a game engine, but also a simulation engine. Unreal Engine has made significant strides in the simulation industry. Its advanced graphics capabilities enhance immersion, especially in aerospace, automotive, and military training. It seamlessly integrates with VR, AR, MR, adding depth to simulations, and its modular design supports easy scaling and integration with legacy systems. The use of Unreal Engine with digital twins and AI increases efficiency in maintenance, designs, and operations. Furthermore, its open source tools reduce costs and making high-quality simulations more accessible and enhancing realism and efficiency across the simulation ecosystem. Over the past few years, Epic Games implemented several simulations key features in Unreal Engine, particularly in their work on important simulation projects. Project Anywhere and Antoinette have been a great inspiration and opened up the possibilities for bringing flight simulation to Unreal Engine. Unreal Engine provides a practical process for developing simulations, from defining scenarios and content to implementing special features, integration, and support for functionality at the framework level. It provides all the essential features for simulation development. As you can see, this practical process quickly has a huge impact on the creation of simulation applications, from content creation to scenario execution and interaction in training. Unreal Engine provides key features for simulation. It is also building a huge ecosystem as it integrates engines, libraries, and plugins for various industries along the core functional feature map, from environment model, training definition and execution, deployment to training result. And Kai also has a large lineup of training systems across multiple areas, from novice mechanics and pilot trainees to elite pilots and skilled mechanics. We provide a structured training system. As you can see on the screen, we have simulators in all areas, from CBT content to full flight simulator, FFS. So, simulation technology has evolved from simple training tools to crucial components in designing and optimizing complex systems. These shifts influenced by advancements in data-driven simulation, and the rise of digital twin technology has expanded the role of simulation from just training to supporting real-time operation. These changes are making me feel do something with new technology convergence. And Unreal Engine has become a pivotal technology in simulation across various industries. Its high-quality graphics and real-time rendering enhance realism, improving the effectiveness of training and testing. The engine's flexibility, supported by open-source libraries and plugins, allows for customization and integration of new technologies, making it adaptable to changing market demands. Modern markets and users demand highly realistic simulation technology that closely mimics the real world, which is crucial for effective training and testing. Unreal Engine meets these expectations with outstanding simulation features. Kai is at a pivotal stage in modernizing its traditional simulations by integrating them with the latest trends using Unreal Engine. This integration has revitalized Kai's legacy systems, significantly enhancing realism and efficiency. This has greatly improved product development and maintenance efficiency. This strategic move is crucial in building a new simulation ecosystem. In this session, we will delve into Kai's use of Unreal Engine, discussing our strategy, challenges, and future vision. First, I have three main pillars: rapid prototype development and interface standardization for integration with the existing system, and platform design for sustainable content development. This strategy is a key approach to building a new simulation ecosystem that leverages Kai's technical strengths and aligns with the latest trends. To remain competitive in the fast-moving market, quickly testing new technologies is crucial. Unreal Engine's flexible and powerful development tools enable rapid prototyping, allowing us to experiment with new ideas or features in a short time frame. A key aspect of this strategy is an iterative development process, which minimizes early failures and quickly identifies promising ideas. Rapid prototyping with Unreal Engine helps Kai respond swiftly to market changes and reduces the risk associated with adopting new technologies. Kai has built legacy systems over many years, accumulating a vast amount of variable data. While these systems remain important assets, seamless integration with newer technology is crucial to unlocking our full potential. Standardizing interfaces for integration between legacy systems and Unreal Engine is essential. This standardization enables legacy systems to work seamlessly with new technologies, ensuring data and functionality interoperability. As a result, Kai can leverage its existing assets while maximizing the benefits of the latest technology. Simulation systems shouldn't be built as a one-time project. They need to evolve and expand over time. To achieve this, a platform design that supports sustainable content development is required. By utilizing Unreal Engine's modular structures and the open source ecosystem, we are creating a platform that can be continuously developed and updated with diverse content and features. This approach allows Kai to easily add new scenarios or features as needed, ensuring the long-term longevity of the simulation system. Additionally, the platform facilitates collaboration with external developers and partners, laying the foundation for building a larger ecosystem. Let me explain the convergence of the Kai and the Unreal Engine. First up is flight simulation. I design a platform to enable the development of sustainable simulation content while developing dedicated components and plugins for flight. The first is the development and make platform details of dedicated components and plugins. The presentation will be continued by Eun-Kyu Lee, senior researcher at Samwoo Immersion in South Korea. Please welcome him.
Hello. It is nice to see you all, and I think this is a great honor to speak here as a speaker. I am Eun-Kyu Lee from Samwoo Immersion in Korea. Samwoo Immersion is specialized in developing education and training system, and many of our solution is developed with Unreal Engine. This section will cover two main topics. First is aircraft control and visualization in Unreal Engine, especially focused on CG interface. And the second is the core concept and techniques for visualization of aircraft in Unreal Engine. The first topic is aircraft control and visualization in Unreal Engine. This topic is consisted with 5 subtopics. They cover the important aspect of core elements for the integration of aviation simulation in Unreal Engine. The most fundamental function for aircraft simulation is moving the aircraft, whether it's driving on the ground, taxiing, or maneuvering in the air. To control the transform of the aircraft in a newer world is the most basic requirement for the integration. To do this, we utilize the interface named CG, the Common Image Generator Interface, which is used by existing image generation devices and implemented some functions in Unreal Engine using C++ to create a function library and convert CG packets to Unreal structures and vice versa. We implemented actors that can communicate with other systems using CG by using the corresponding actor components and develop them in a reusable form by packing them as a plugin by their functional units. By utilizing these, we have integrated a basic system that controls the core functions for communication between aircraft simulators and image generating devices supported by CG, and have been developing to expand the core features based on them. Most objects are represented in an image generating devices, including aircraft. They are called entity in CG, and the packet to control them is the entity control packet. Each entity has not only basic function of updating location data that based on whether it is relative or absolute, but unique properties such as rotation, scale, or opacity. These properties can be controlled and updated by Unreal Engine as it receives the entity control packet. The example is the opacity of aircraft is changed by the properties named alpha is controlled. The function of reflecting articulation data received via CG packets to an entity can be implemented using anim blueprints. A packet called articulated part control is defined in CG, which allows you to set properties such as parallel movement or a rotation of predefined articulated part of an entity. This example has been developed to receive the transformed data from packet and control the rotation value directly from the data. While the entity control packet contains properties that control the animation state of an entity, it is usually more convenient to use art part control to independently control the animation of the various articulated part in an entity. By defining a unique property of the art part control as animation time, it is possible to procedurally control the animation using the evaluate node. This controlled animation is then blended with the state of the other articulated parts using layer blend per bone node. There are some properties that cannot be controlled by entity control and art part control. A packet that allows control of those properties is component control packet. You can define which operation to be performed when you receive this packet with component type and component ID. The example shows some curve presets that define several flashing patterns for the exterior lights of an aircraft. Flashing patterns are changed by replacing these presets. We have implemented a feature that allows you to attach and detach weapons such as missiles from entities via component control. The presence or absence of mounts for attaching weapons, as well as the type of weapons, they can be controlled and changed using the component control packet. And aircraft simulations use various internal properties such as atmospheric conditions, the aircraft aerodynamic properties, and fuel levels to control flight state and aircraft movement. However, when the aircraft needs to interact with geometry on the ground, such as takeoff and landings, the image generator must generate provide that animation. The line trace feature of Unreal Engine can be used to continuously measure the distance from the ground to a specific point of an aircraft. To inspect the information such as height of terrain, height above terrain, and line of sight, such as to be communicated to the aircraft simulator in CG packets. The next topic is developing features beyond CG. That covers the process of implementing features in Unreal Engine to make aircraft more realistic and responsive to interaction. Unreal Engine provides PBR materials to generate realistic surface materials. In addition to the material's reflection of light source performed on the surface, post-process features like bloom or screen space, ambient occlusion, and more also provide more realistic visual effects. The material graph of Unreal Engine provides an interactive and intuitive user interface, so it makes to design procedural patterns that can be applied to materials easily. Material instances also allow for the creation of editable copies of materials that could be easily controlled manually. The scene texture node provides by Unreal Engine. It allows a specific layer in screen space to be used as a texture. which can be used to detect specific area in screen space and restrict the rendering of surface materials to the inside of those area. So making it possible to create the HUD that resemble HUD of real world. While it is possible to design and control complex procedural patterns with unreal materials, it is often more convenient to use widget blueprints to create images that are complex or contain large amount of numerical or text representation. Widget blueprints can be used to a widget component into the world and also can be imported as render target for use in surface materials. Unreal Engine also provides a feature called meta sound that allows you to procedurally generate control audio beyond simply playing and controlling the existing audio assets. This allows a noise that basic waveform to be generated and combined to create a wide variety of audio, and procedurally generate filter effects can be applied even when playing the Vive assets. So let me play some audio in this place. This is the engine noise of the aircraft, and it is designed all procedurally by the noise. And metasound graph can be reused in other metasound graph as a node, and it is possible to create Morse tones with complex duration and interval control of simple short frequency waveforms. This is completely procedurally generated, allows the audio tone, duration, and interval to be controlled dynamically as separate properties. Let me play this again. This is also procedurally generated. And Unreal Engine can handle input from hardware using a raw input feature, but there is a plugin called Control Assist that is more convenient for handling multiple devices simultaneously. This can be used to simplify the hardware setup, which can vary for the types of aircraft models, and make it simple to process the corresponding signals in Unreal Engine. Anim Blueprint in Unreal Engine also for efficient control over the animation of skeletal meshes, such as previously controlled aircraft articulated part in animation. Controlling virtual cockpit is also very convenient using the Anim Blueprint. The animation blueprint receives processed input from the hardware as key value pairs. So utilizing blueprint interfaces or derived blueprints from Anim blueprints allow for more reusability and structural flexibility. The georeferencing system makes converting the location simpler. So rotation requires some merging of rotation values because it must be calculated relative to the ellipsoid normal. But the conversion can be done by merging the ellipsoid normal and the rotation value corresponding the north, east, and up. Using this, it is possible to express the position and rotation of an entity in the unreal world based on its latitude and longitude and altitude in a simple procedure. There are many ways to represent terrain in Unreal Engine, but due to the nature of viewing terrain from high altitudes, it is necessary to implement a spherical representation of the Earth. We use Cesium, one of the many terrain surfaces compatible with Unreal Engine, to stream terrain into the Unreal world. Streaming data imported as raster images is merged through a layered material that has different rendering methods for different type of data, just as layers are typically used in GIS, the Geographic Information System. By defining the layer blend property of this layered material and the material layer, it is possible to represent different textures on the part of the ground area.
Okay.
This is the end of my part.
Okay. Thank you, Ngü. Yeah. The third is the adoption of large-scale tactical training through the development of AI agents. Using Unreal Engine to rapidly create prototypes, we are working with the South Korea Air Force on a rapid research project to enabling a large-scale tactical training on the Korean Peninsula field. The AI agent created will allow our Air Force pilots to perform a variety of tactical exercises in an extremely realistic environment. As you can see on the screen, there are AI agents trying to combat with our pilots. There will be, chef layers and AI agents coming and through by. Yeah, this video contains sensitive information, so let's move on. Yeah. Thank you. Yeah, and let me introducing a new approach to spatial digital twins. Traditionally, the simulator industry has relied on 2D worlds created from satellite imagery and altitude data. Later, 3D worlds were incorporated through modeling for certain flight references, but this was insufficient for creating digital twins of large urban areas. So we shifted our focus to ultra-precise wide area digital twin technology using drones and discovered an effective solution. This solution delivers 8K resolution textures and 5 centimeter imagery, utilizing GNSS GCP technology to produce digital twin maps with an error margin of 5 centimeter or less. This photography and next one, digital twin map is 2 centimeter. And utilize the RTK GPS to get precise location information. We also automated mesh generation and texture creation during the build process. Our digital twin technology to maximize coverage while minimizing error. Tactical innovation in South Korea's solution have solved the problems that existing digital twin has had: precision, efficiency, scalability, realism. The world's only spatial digital twins platform company based on high precision, high resolution scanning by drone. As you can see on the screen, this is a new approach to supporting fast-moving spatial digital twin market needs. This old one is become this new one. Tactile Innovation's solution involves matching PSM. PSM is photogrammetry software mapping. PSM wide area scans with real-world coordinates and drone GPS. This process enables fast and accurate creation of wide area geometric digital twins by converting pixel information into cloud data, generating meshes, extracting textures, and automating DSM. By using the most precise construction method available, this solution creates the most realistic digital environment possible. This solution has more than 95% match rate with actual data, and more than 80% resource saving rate, and more than 90% maintenance cost reduction rate. And this is a usage of digital twin solution for simulator and testbed. There's a lot of simulators. And also, this digital twin solution is using for many places, urban blueprint and monitoring, and risk or disaster simulation, and so on. So, as you can see on the screen, we make a VR-based helicopter simulator prototype with an Unreal Engine 5.4 version and digital twin solution. It took us just 2 months for a flight like this. I believe this result is a strong case for leveraging the platform. Here is a nearby Seoul, which is our capital city. There are many buildings and many construction sites and environments. Yeah, moving on. And next is N-display and mosaic technology as clustering computers to enable multi-channel, multi-display flight in an ultra-accurate, low-altitude digital twin environment. To supporting multiple video channels, traditional simulators have provided multi-channel by lacking video computers for multiple channels. With the possibility of multi-channel configuration utilizing multiple GPUs on a single computer with today's computing power, I've been researching and developing end-display and mosaic recipes that allows for multiple multi-channel configuration using up to 8 GPUs on a single board via clustering computer. What you see here is a multi-GPU setup on a clustering machine to handle 3 channels. And next up is maintenance simulation. Similarly, in the field of mechanic simulation, we thought a lot of how to efficiently build a content pipeline to continuously produce high-quality content. In addition to building realistic content, we developed and introduced a user interaction system that prioritized user experience and game features and task system for sustainable content creation. The presentation was made by Soo-Jung Kim from Vive Studio in South Korea. Please welcome her.
Hello, I'm Soo-Jung Kim from Vive Studios. I'm a developer currently working on VR project for aircraft maintenance. Today, I'm going to talk about building a maintenance simulation platform. But first, let me give you a brief introduction of Vive Studios. Vive Studios has grown over the past 20 years, working on immersive content like AR, XR, and more. And we have built a strong edge in the industry with our advanced technologies. The main goal of this project with Kai was to create a maintenance simulation that helps train aircraft mechanics and act as a platform that can improve over time. To achieve this, we focus on 3 key elements: high-quality simulation, an intuitive user interaction system, and a scalable platform. It's important to create an experience that mirrors the real work environment, especially for mechanics who have complex tasks. Training on actual aircraft repeatedly is challenging, so realistic immersion in VR is essential for effective training. We created ultra-high resolution textures using CATIA data with millions of polygons, optimized for a real engine. By combining this with real-world aircraft pictures, we captured both the interior and exterior to give mechanics a real visual experience. Using Unreal Engine's material editor, we depicted materials like metal, glass, and plastic in a realistic way. We also used virtual textures in Udin format to optimize AK textures so users can feel like they're working on real aircraft parts. The environment and various toolsets were carefully designed to provide a realistic experience of the maintenance process. We included detailed animations that mimic real-life maintenance situations. To achieve this level of realism, the team needed a system that could handle large amounts of data in real time. Unreal Engine made this possible. To bring maintenance procedures into a virtual environment, we analyzed the maintenance manual and focused on the key elements. We simplified the procedures and reduced complexity to make them easier to follow. This process involved understanding the mechanics' needs and work environment. We aim to reflect the real maintenance process in a virtual setting. The original manual presented the maintenance process as a simple sequence of actions without highlighting the importance of each step. When we moved this process into the simulation, we redesigned the task to highlight the key actions. For example, we simplified their work process by reducing unnecessary steps. We also adjusted the information based on the mechanics' skills. Skilled mechanics could focus on their main task, while less skilled mechanics had an option to hide unnecessary tasks by clicking one button. This approach allowed mechanics to develop practical skills in a virtual environment, while learning at their own pace. One of feedback that we received from the mechanics who previously used the VR maintenance was that they said warning sign and notifications were distracting. To solve this, we simplified how information is delivered. We use 3D widgets to show task steps and tool info, but we keep it simple so that they only appear when needed. You can easily turn this information on or off with a button, which helps keep the screen clear. We also added haptic feedback to signal each maintenance step, and we made sure that the simulation doesn't move forward until all critical tasks are finished. Tasks can be automatically accepted or must be accepted once specific conditions are met before they can be considered fully complete. Lastly, we created an efficient content pipeline to maintain and scale these high-quality contents, which I will explain next. When developing our maintenance simulation environment, we focus on scalability and sustainability. To handle different scenarios and to keep trainees engaged, we have created a system that combines Unreal Engine's gameplay message system and game features with our own task system. For this project, we needed to manage many parts and data inside the aircraft more efficiently. Some had to follow a specific order, while others were more flexible. To handle this, we had to use flexible systems, which are gameplay tag and currently beta gameplay message system. The gameplay message system lets you register and send messages among the objects that are not directly connected. Instead of using the event dispatcher, we implemented an event-driven system based on the publisher-subscriber architecture. In this system, publisher broadcasts events without knowing who the subscribers are, and subscriber can receive specific events without needing direct reference to the publishers. This enables a more efficient and scalable event handling within the system, making task management much easier. We got this plugin from the earlier engine sample project, Lyra. It's still in beta, but it offers a lot of advantage. It helped us simplify the flow of events and made maintenance easier. Because of this, we could manage the complex interactions between different components more efficiently. Each message channel in the system uses a gameplay tag from Game Ability System, which can be managed through a data table. This setup allows the system's components to work independently but connect without any difficulty. Gameplay tags make it easier to manage and scale. Its flexibility allows us to add new parts or features without disrupting the existing setup, helping the system to grow over time. The task system, which I will discuss next, was designed to organize and manage the simulated maintenance environment. It used a scenario-based Unreal database to manage tasks assigned to trainees and track their progress. The database contains information like activation conditions and completion requirements for each task. Using this data, tasks are assigned and their progress is monitored. The task system was designed with a modular approach. Each task is a self-contained module that can be easily added, removed, or modified for different maintenance scenarios. We used game features to manage these modules in a dynamic way, enabling or disabling them as needed. These task systems are built as plugins and depend on game features, allowing them to be used independently. You can also set plugin dependencies by editing game features on the plugin pages. This has improved the system's flexibility, and its scalability allows new tasks or scenarios to be easily added to existing structure. As a result, the development team has achieved more in less time, leading to clear improvements in both project progress and work efficiency. The combination of Unreal Engine's plugin system and the task system has allowed us to build a strong framework for organizing and expanding the features of our content. Since both systems are designed to be modular and flexible, it's easy to add new features or change existing ones. For example, when new training scenarios or tasks are needed, they can be easily added to current system. This allows us to quickly adapt and provide content that meet the needs of trainees. To make it even easier, we are using Unreal Editor scripting to develop an intuitive user interface. This lets non-developers use the task system in complex maintenance situations. We customize the editor so that non-developers can create and modify tasks as easily as using visual scripting. This system allows task scenario to connect smoothly with maintenance actors, and it works without the need for complex coding, making it intuitive to use. This approach had maximized efficiency during both development and maintenance. Looking ahead, we plan to further develop this system so that non-developers can easily reconfigure maintenance simulations with just a few clicks. Our ultimate goal is to reach a point where anyone can easily build and manage simulation environment. Here's a video showing a VR simulation developed with the features I just explained. By combining various features of Unreal Engine with the task system, we have created sustainable content that allows trainees to set and achieve new goals continuously. We have also created an environment where non-developers can easily manage and update the system, maximizing efficiency in development and maintenance. Also, this system was developed for aircraft maintenance simulations. It can be also adapted for use in various industries, such as manufacturing, healthcare, and education, providing efficient training environments. Its scalability and flexibility make it easy to customize for a wide range of scenarios, and it plays a key role in the diverse content developed by Vive Studios. We plan to continue enhancing this system in the future. Thank you.
Thank you, Sujal. Our last chapter is vision. The current simulation ecosystem is actively adopting virtual reality, similar to recent changes in other industries, and is utilizing high-resolution graphics and 3D modeling to provide a more realistic simulation environment. And the simulation industry of the future will leverage AI and big data to deliver personalized training programs and performance analytics. And with the cloud-based simulation greatly improving the accessibility and efficiency of remote training. In particular, the cloud will enable high-performance simulations to be run from anywhere, enabling training without geographical restrictions, and real-time collaboration will allow multiple users to train in the same simulation environment simultaneously. The ability to instantly apply the latest software and data ensuring consistent training experience. Additionally, advances in wearable technology allow for real-time monitoring and feedback using biometric data. This enables personalized feedback for learners during training and allows for immediate adjustments to enhance the effectiveness of safety of the training. And what is the future direction of KAI? Answer is very simple. It is all about platform and ecosystem. With the results of the current integration, we will further enhance the platform and ecosystem. As I mentioned, that Unreal Engine is a simulation engine. And with the amazing results we've seen here, we will be leveraging it even more to develop our own aviation simulation engine with Unreal Engine. We intend to build a simulation content pipeline that can generate content with high quality and high speed through the Make platform. And we are also developing the platform to maintain and develop a sustainable ecosystem in South Korea's simulation industries. I want to see these changes go global and turn the simulation industry around the world into large and healthy ecosystem together. Unreal Engine's role in the present and future of the simulation industry and the new ecosystem of simulation content that KAI envisions will be critical to the health and richness of the ecosystem. We continue to use Unreal Engine as a simulation engine. And we are participating in the ESEC exhibition in Orlando on December 2nd this year. You can experience and discuss all the projects introduced today with me, and please come and join us. So that's it for our presentation. I'm sure there will be a lot of questions. So in order to make our short Q&A time more useful, I'll be taking questions after this session. I will stay in front of this room. So please come and see me and ask me any questions you have. And thank you for your time. Enjoy the Unreal Fest. Thank you. 감사합니다.